Hello. Mute your microphones. Ask me as many questions as you can.
We'll say something.
So how is everyone doing with the labs and everything? Good. If you need help, don't hesitate to reach out to me. Okay, we can spend some time discussing. Praveen, maybe you can chat about the discussion we had about labs. Was it helpful? How did it go? Maybe you can put it in chat. I spent some time with Praveen the other day working on labs, so maybe you can share a sentence or two about it, Praveen.
So it's coming from the machine.
Okay, I guess we should, it's 2 minutes past, right, Manish? We should start slowly?
Or yeah, we should get started. Yes, it's already 10:02. Let's get started.
Okay, so we are in the last session of our course. This session, I tried to pack it with as many goodies as possible. I want this session to be also interactive because you guys can guide me in terms of how much detail we need to go through. Okay, so please keep me posted. I see some people still continuing to come in. Okay, so what are the topics we want to discuss today? So the $1 million topic, I guess, for today is this thing about object-oriented programming. We will spend a good chunk of time today talking about objects. And my original plan for this course was not to spend too much time on objects, but as we went through, I realized that probably this will be something you will encounter right away and you're using objects all the time. And so we must address this. What you can really contribute is as we go through this, you can either speed me up or slow me down based on your own experience, right? If you know stuff, you can speed me down. If I'm going too fast, you can slow me down. Okay, but at the end of the day, object-oriented programming is an amazing field. We could spend an almost entire course just discussing how to do that, and Python deals with objects in its own special way, and I will highlight that quickly for you. Then something we left untouched, we did not explore this intricate world of strings very much. I don't think I'll spend too much time on it, but I'll give you a flavor of some string manipulations and draw your attention to string processing. It is a surprising thing that a major portion of our code very often deals with handling strings. So we have to talk about it. And then the last topic that we were told would be very interesting to all of you is this topic of version control. So I will spend some time on version control as well, how to use something like Git or GitHub. So those are the three big topics. I have actually added just now a small section on how to deal with exceptions in Python. So let us see if you have time. I will talk about it. Otherwise, at least you could probably read about it. Quick update in terms of quizzes and labs. I think that's something that many of you were asking about. I sent out an email. I've added it to the course updates page, but it's probably worthwhile just quickly talking about it now. I cannot stress this. I've repeated myself a few times, but the goal for me is that all of you take time to write code, design code, deal with failures, fix your code, test your code, right? It's all about some kind of proficiency, right? And it only comes with a lot of practice. And I'm here to help you if you experience any challenges. What is fantastic, and I want to congratulate all of you, is that you have shown me that you are able to stick through a course of 7 or 8 sessions, commit time to do labs, etc. That is a tremendously powerful skill. So I want to congratulate all of you for making it this far. But of course, to put the icing on that cake, you must continue to write code and practice. Okay, and I cannot stress that enough. So please make sure you carve out, even now, if in the next 2 weeks, there's plenty of time. If you do an hour a day, you can make a lot of progress. And in this next 2 weeks, you have me as a resource to help you. If there's anything I can do, I'm always there and available to help you to work through any issues. So in terms of quizzes and labs, I will reopen all the quizzes and labs. And so you can continue to go back and take your quizzes and labs. If you have any problems, just send me an email. I will look into it and make sure it's okay. So you have until March 15th to finish all the quizzes and labs. And after that, we will collate all the grades, and we will send you certificates of completion with your grades in it by March 22nd. Okay, and the overall passing grade for the course is 60%. I want to really downplay this number. Do not set your targets on it. But of course, it's a number that some of you wanted to know, so I've put it here. So that's it in terms of announcements. Manish, did I miss anything?
No, I think we should get started with today's session. There's a lot to do.
Okay. If any of you have questions on this topic, of course, just on in terms of logistics, just let me know. Okay. Okay. So quick poll, I guess. How familiar are you with object-oriented programming? So maybe you can pick one of these options. I'll give you like a minute, and then we'll see. By the way, is the font on my screen okay? Can you all see it?
I think a font bigger will be
better.
Yeah.
Okay, so let's see what happened. Okay, 50-50. Okay, so this is interesting, right? So here's what I want to say, since it is kind of split. And there's some of you who are very familiar. So those who are very familiar, please chime in and open up your microphones and share your experiences. For those who are slightly familiar, I will try to talk about some Python specific ideas of object-oriented programming and highlight some of the interesting features and maybe potentially advanced or dusty corners. And for those who are not familiar, I will just provide some basic information as well. Okay. So that's good. Thank you for the input. I will use it as we go along. So just wait for a second for my page to, okay. So what should I say in terms of introduction? Okay, first of all, I think that so far we primarily worked in a world of functions. We wrote functions, we used data structures, we passed data to functions. But somewhere under the covers, we did use objects in the sense that in Python, everything we create is an object. An integer is an object, a float is an object, a string is an object. But we didn't consciously think of them as objects and manipulate them as objects. So today, as we go through this, it's nice to look back at everything we did and say, oh, I was actually using an object, and is there anything I could have or would have changed? But of course, the world of object-oriented programming says, if you look around you in the world, almost all of your interactions with things are with objects, right? You drive a car, it's an object. And we have some kind of implicit contract with every object in the world we encounter. This will take, if I go into this topic, it's a very beautiful topic. It's called design thinking. There's some very natural things we do. For example, when we see a door as an object, we expect to see a handle somewhere. And we expect to push it in a certain way to open it. And push and pull sometimes are even culturally defined, but we have a natural expectation of how objects should behave. And they're called, in design thinking, they're called affordances. Okay, so we live in a world with objects. We have natural expectations of how they should behave. Sometimes we learn about how they should behave. So when we encounter a car, maybe a good example, when we have never used one, we don't know much about it, but then slowly we understand every car probably needs some mechanism for steering and some way to control the speed and so on and so forth, right? Speedometers. So there are many behaviors that we expect of our objects. And so the million-dollar question for us as we started writing programs was to say, why don't we just simulate that same behavior in our code? Why don't we think of everything in our code as somehow being an object, which has its natural interfaces, natural ways that we interact with them, and all will be well, right? we seem to be relatively successful in, like, say, a field like engineering, where we take a lot of objects, we connect them together, and suddenly you have, a plane or a robot. Could our software be similar, right? So that is the big buzz of object-oriented programming, right? And so let's just go ahead and, this is abstract, so think about it. But of course, I will try to make this now hands-on and concrete. So first of all, let's do a simple example. So we need, one of the beautiful things about this is it's mildly abstract, but it forces us to ask about structure. And I spent a little time brainstorming with Manish about maybe a nice example. Now, I have to be very candid with you that it's hard to come up with really good examples at an intro level, right? When you go into something like the world of finance or the world of biology or the world of chemistry, there are very elaborate natural object structures or class structures in those fields. They're big, they're large, they're complex, they're hierarchical. But when we come up with small examples, there are 10 lines or 20 lines of code, we tend to do mildly inane things. But hopefully they just illustrate the principle, okay? So for our example today, we will work with a simple Python library that deals with two-dimensional shapes, right? Later, you can even think of connecting this to a graphics library and so on. But for now, we'll just have some properties of shapes and we'll manipulate them. Okay, so what's the natural structure when we think about two-dimensional shapes? Well, we have already classified them in some ways and given them even names, right? So the shapes we will discuss today are the obvious ones, say circles, squares, rectangles. And they have some, so what is beautiful about this is we start thinking just like the real world is in some sense, or the world of two-dimensional figures is. So I'm sharing an insight about how we create code. I spend, whenever I work in a new field like finance or accounting, I spend a lot of time saying, what does the real world look like here, right? And the more you can absorb it, the better your software comes out. So anyway, here you go into this world and you say, well, there are circles. And you say, what is a circle? Okay, you can define its shape, but one of the key properties of a circle is that it's characterized by one number, which is its radius. Okay, so we want to start modeling the circle as a thing that has a radius. Similarly, for square, it has one number, which is the side. Rectangles have two numbers, and so on and so forth, right? So you can build up your picture of this domain. But now we want to write some code to model this domain. And in particular, we also want to say, okay, they have properties, but they also things that can be derived, almost like behavior. You can ask a circle, hey, how much area do you have? Right? That would be a nice thing to do. But that is modeled in, as we know today, in functions. So let's look at our code quickly. Is the code big enough? Can you see? Can all of you see? Do you want it bigger? Maybe I'll just make it. Okay, that's probably better. Okay, so what can we say here? So first of all, I took a simple path. You guys, all of you can try this out and make it, more elaborate if you want to. But the simple path I took is I said I'll model a shape as a tuple. So there's some natural reason why, because we want to keep these shapes kind of fixed. So instead of making a list, I made it a tuple. And I said the first element of the tuple will be just a string. That is the name of this shape. And then I will add extra slots into this tuple, which correspond to things like the radius and so on. Okay, so here you go. I have 3 shapes already defined. And then I can put them all into a list. So I can manipulate them all together, right? And then we do a simple thing. I want to write this get area function. And this get area function is kind of interesting. It can get the area or compute the area of any shape. But the way it does it is it has a switch here. You could have written this with a switch, with an else, various things. I just put some if statements here just for you to see it. But the logic is very simple. I need a switch that switches the function, the calculation, based on whether you're a circle, a square, or a rectangle. Right? And then if you run this code, I just put a loop here, and this code will just loop through and compute the areas of all the shapes. If you can tell me on chat, I would love to know, if you were given this problem, is this what your code would look like? Let me take 30 seconds and see. How many of you think your code would have come out like this? Or it would look very different? Anyone? Anyone? Would have used if else if. Okay. Okay, but structurally, I don't know whether all of you would have gone to tuples or, you know, you're just used a variable or something. It's unclear. But anyway, this is a metaphor, right? So now I'm going to switch metaphors and I'm going to switch to the world of objects. Okay. So the first thing we have to say is, okay, I would like to pretend that all 2D figures are objects. And before I do anything more, now I have to make a definition. So what is an object? Okay. And this definition is a two-tiered definition. An object is the instance of a class. So then I have to tell you what is a class. And a class, in programming at least, a class is also synonymous with the definition of a new type. Right? So far in our code, we have only been consuming types, integers, floats, doubles, etc. We never created new types. So we were always using types which were pre-created, and we were using, which were happened to be classes, right? So if you say what is the type of an integer, you're going to see that it's a class. It's a class, it's an instance of the class integer. Okay, so now let me recap. So class defines a new type. This type has some structure and some behavior. And then using this class as a template, we create or we instantiate objects. Right? So every instance of a class is called an object. It takes a second to formalize this. When I first learned this, I used to flip the two around. I would never know which comes first, the class or an object. Okay, so you might want to fix that in your mind. The class is definitional and an object is an instance of a class. Okay, so much for theory. Let's just go and make a class, right? And what is really cool in Python, and those of you who have used some other languages, you can contrast this with your experience in other languages. In Python, making a class is no ceremony, right? It's literally this. I could just say class. So the keyword that you have to learn is class. And you can name your classes. And then you really don't have to provide any body at all. So you can say, well, what is the use of this such a class? And let me just show you what you can do. First of all, you can create an instance of a class. So this, what looks like a function call, is actually a constructor, right? By default, all classes have constructors. We can spend a whole discussion about constructing classes. But for now, if you just say circle, open parent, close parent, that is a circle constructor, and an object C1 will be created for you, right? So let me run this code and I will talk about, you know, what you can say. Okay, there's a lot of information here, but let's just look at this part of the code. So I'll just move it up for a minute. Yeah, so you can see this right on top. So if you look at the type of circle, which is the first line, you see it say Python knows that it's a class, right? And then if you look at the type of the object, it says it's an instance of the class, and this main underscore dot circle is telling us that it's an instance of a circle. Okay, and we'll talk about these underscores in a minute in more detail. Okay, so we created a class, but what is really interesting is the class actually here behaves like a property bag or a container. And you can add any number of variables to this class dynamically. You haven't pre-declared that a circle has a radius, but you can assign some new variable as a variable of the class. And this radius will actually be a property of this class now, right? This is a behavior that's peculiar to Python. It's a very dynamic behavior, but it's not necessarily clear why we would want to do this. Okay, so I would like all of you to go away and think about whether you'd want to use. So it's a kind of, sometimes when we work with very constrained code, there is no flexibility, right? And if you want to change the code, you have to go back to the circle definition and change it. But Python can be very dynamic. You can dynamically add properties and methods to a class. And we have to ask the question, when would we need that in our code? Okay, and then it's, you know, it's a double-edged sword. It can be good and it can hurt, right? But I just want to highlight this very key difference, because this is not the behavior in Java or C++ or C# or any such typical object-oriented language you might use. Just like we can add a property to a class, you can add a function or method to a class just by assigning. Okay, and this last piece of code here just simply runs, you know, runs the calls the object and gets the area and so on. So just take a minute and play with this code. Make sure you understand how it flows. If there are questions, ask me, even now or later. What happens if you try to print your object? Yeah. So, okay, so you see, okay, so did I print it? Yeah, very good question. Thank you so much for asking that question, right? Because, okay, so let's just do print C1. Did I do print C1? Okay, so let's just do print C1 right on top. And let me clean up because I'll take off this extra stuff. Thank you for that question. And we are going to spend a little moment looking at this, right? So when you do print C1, it's going to do something interesting, right? You see this third line here? It actually shows something, okay? So what happens? I'm going to go in detail into what happens. Python says that when you say print C1, you're basically, the print function is telling C1, can you make yourself look like a string, right? It has a natural, or is there a natural stringified representation of the object that I can use to display something to the user? And by default, there isn't much. Python creates this little string by default, which is not very useful, right? The only thing that it says is, well, C1 is a circle object, right? Which is nice. It's nice to know it's an object, but it doesn't tell you what is its radius and other properties. So one of the first things we might want to do when we start creating objects is to create good stringified representation. Now that becomes an art, but I'll show you how the machinery works. Did I start to address your question? We'll just make sure that you keep this question over the next couple of pages. I will go through this in detail. Okay. Okay. So we have created our first objects, but it is not very. The type is not very strongly defined, right? Some loose idea. It's like a namespace. I stuff some properties into a container. Not very interesting. But now we can say, no, we will actually make our type much more rigid. We will create a constructor, right? So that, this thing here that took no parameters, like when we said circle, open parent, close parent, it took no parameters. Now we will force you to provide specific parameters that will make sure that my type is appropriately constructed. So how do we do that? Well, so now we start to really do some class construction here. Again, I probably have to make this a little bigger. In case I forget to change the font or you're having any difficulty, please post in chat or something, okay? I'm trying to manipulate the code and make sure everything's easy for you to follow. Okay, so notice here, this is called the class constructor. And unlike other languages, in Python, the class constructor is defined by $_init $_. And if I take a moment to talk about it, there's a lot of magic in Python which is related to double underscores. Okay, and there's a short form that Pythonistas use. They call them dunder methods, $_ methods, right? So dunder methods are dark voodoo, right? Secret sauce that makes Python work. Of course, init is not dark voodoo. I think everyone has to learn about init right away, because you want to construct classes, but later you'll see there are other methods that can do all kinds of powerful things. And the question about print will come up in a second, okay? So I covered this discussion here. So what do we have to do to make a circle with a specific radius? You have to create an init method. The first argument for every method in Python has to be self. So in other words, every method takes a reference to itself. And that's how when we set a value, this radius, so it's assigning. So you pass in a radius here and it gets assigned to the class instance. Okay, this is a little mechanism. I'll give you a nice visualization in a minute, but let me just talk you through the mechanics of the construction. For those who are slightly advanced, take a minute and think about, what makes classes construction well-defined? How do you handle, classes that are not ill-defined? What is a good constructor, etc. Okay, but anyway, so first parameter is self, and then you take self and you assign the properties to self. Okay, and that completes your class definition. So if you had other properties, you would simply just add more parameters. You'll see this with the rectangle in a minute. You'll just add more parameters and assign them all to self, and then you're done. Okay, and after you're done with this, you can just instantiate it. But now notice it takes one parameter. And also notice that the self parameter is automatically populated by Python. Okay, so it's interesting. You only need to provide one parameter. And this automatic population of self is the mechanism by which Python will actually decide which instance to create for you and which method to call for you. But again, you don't have to worry about that now. Just use it as a prescription to create classes. Okay. I'm not sure my microphone is working right now, so if you want to say anything, just chat me. Okay, I've switched off my sound for a second. Okay, so now we go ahead and say what we say. Okay, I want to call your attention to some. Okay, somebody asked self.radius equals radius. Can you explain that again? Okay, yes. So very simple assignment here. So the radius on the right hand side is a parameter, right? It's coming through as a parameter, and the circle is a new property for the circle is being created. This is now an internal property, or the left hand side is an internal variable of the class. So self.radius is actually an internal variable now of every instance of the class. So my words, I'm choosing kind of carefully. Every object of which, when you instantiate circle, every object will get a new variable, which is called the radius, which is inside the object. Okay, this will become natural in a second. So this is a variable that's inside the class, or inside the object actually, and this is a variable, a parameter that comes in. So so after this, so I will show you this in a picture. I have a picture below. I'll show you a picture of this in a second. Okay, so just hold the thought. So the parameter 5 is now stored inside the circle. Where is it stored inside the circle? It's stored in a new variable that lives inside the circle. It's called the circle's radius, right? So it's a property of the object. Okay, and you can actually get it out. So if I run this code, you can see on this line, we created the circle here on line 8, and now I ask the circle, can you please show me what is your radius? And it says the circle has radius 5. So that's the first printout that we see. Okay. Hopefully that answers your question. Just hold it and we'll go through. I'll show you some pictures as well in a second. Okay. Okay. So the next thing we can do is, okay, we have, so we're going through some design here. We're saying, okay, fine, we created one property. So what? Now we give it some behavior. So this is the next thing you do. We add a function to the class. Again, notice every time we add any kind of function to the class, whether it's a dunder method or a regular method, you always have to have the first parameter self. This gives that function access to the right instance variables and so on. Okay. And when you want to do a calculation, of course, the formula for the circle is pi r squared. When you want to do a calculation, you have to use some radius. But notice this function does not get radius as a parameter. This function goes to itself and says, hey, I am inside the circle. Show me what my radius is. So self.radius. So self now starts becoming natural. When I am doing as a function inside a class, when I'm doing work on myself, I always prefix my variable names with self. And the magic of Python is that it will route the call to the right place. So there could be some radius outside the class definition and the object instance, but this function will always get the locally defined radius. So that means whatever value is set here is exactly what will be used when we compute the area. Okay, and this is the key mechanism. The key mechanism of object-oriented programming, right, is if you give an object various properties like radius in the constructor, then when you write methods, you will automatically use the locally defined values, and the rest of the world cannot affect you in any way, right? So you're kind of encapsulated or isolated from the rest of the world. Okay, so therefore what? Therefore we can instantiate the circle, and now we can compute its area. Okay, and you will get some answer. If the formula is correct, the answer is correct. Okay, so now can we do more? And now this is the first, and now this is a more elaborate answer to the string representation. So every class in Python has a default __str method. And we saw earlier that if you just say print, the default method is called, and the default method produces a message which looks like this, which we said wasn't very interesting because it was not very descriptive. Now we get to remedy that. You create your own __ str method. Again, you pass in self as the first parameter, and you can pretty much construct any string you want, really. So I encourage all of you to play with this, but you can construct any string that you like. And what is cool now is if I run this code, you see in the last line, when I said print C1, I got a nice customized message, right? It told me I have a circle, it has a radius, it has an area, blah, 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 right? So suddenly you've seen the power of this structure, right? You can create objects, and then somehow these objects have now been given the power of converting themselves into strings. Now you as a designer who writes the code has to think what is the correct information to show to someone when they call print C1. Okay, so does that start to articulate what print C1 does and how __ str can be used to create customized messages? Is that, I know we'll ask this question about what does print do, but now is it adding more color to this? We will refine this a little bit more, but for now, is this clear? Does everybody start to see how you can create a class? Okay, so this is mechanics, right? How exactly to create a class, how to add properties to it. And now using the magic of dunder methods, you can customize what print will show you. Can someone say in chat, Will, or anyone else? Is this clear now? At least can you create your own classes at this point? Okay, good, good. I'm just, for those who are advanced, yes. Just write some extra classes or shapes while we go along, right? Your place to write code. So yeah, if you wanted to add circumference directly to the init, yeah, yes, you can. All you have to do, okay, so that's a good question, right? So if you wanted to add it any more properties, all you do is just do a comma here. So let's say you would do this, and then you would add a new line here where you would say self dot, and you could call it anything, right? I mean, it's just a convention that I use so I don't get confused to call the inner variable and the constructor parameter the same thing, right? You could have called self.c equals circumference. I mean, hopefully that's not an issue. Or you could have called it whatever you wanted on the other way, right? You could have called this parameter c, and then you could have called whatever, right? So you see what I'm saying. So as long as your names are clear, so here's an interesting thing. These names are very important because that's what the consumer of a class is supposed to know and so on. And you communicate about the interface very much. So choose those names carefully. The inner names are less important, but again, we'll talk about later when we expose some of these inner properties, right? So if you called it C, then somebody using your library, he wants to get the circumference back, he won't know it's stored in a value called C. So of course, all the good naming conventions that we learned with variables apply here. Hopefully that answers the question, okay? So, okay, so what are we doing now? So now, while I was describing all this, for those who looked ahead, this is something I will not go through in very gory detail. Please chat me questions, okay? I have, my microphone is not working, my speaker is not working this second. So what do I want to say here? All I've done is I just repeated this, right? So this idea now becomes a blueprint for me to create multiple classes, right? And just to stress again, this is a class definition. Every time I do something like this, I say circles, C1 equals circle, that's an object. It's an instance of a class. I can create multiple instances of a single given class. That's just language, takes a little time for it to become second nature, but I will just keep repeating it a few times so it feels sensible. Yeah, that I have to make this comment, but when I was younger, there was a discussion about how do we learn things. And I thought that, okay, we're having this discussion. I said, it is by understanding. And somebody told me, no, we never understand. We just get used to it. Okay, so something to ponder. Do we just get used to things or do we really understand things? Okay. And there are certain things in life, I guess, we just get used to, right? Anyway, philosophical comment. Quickly, all of you can look at this code while I was talking. For Will, you can see in the rectangle case, I used rectangle specifically to show that multiple parameters can be there pretty naturally, right? So you can have as many parameters as you want. and your classes can get built. Now for the, okay, so lot of typing, right? We did that in a couple of lines. We create a couple of tuples before, blah, blah, blah. But now let's use this to do the same problem that we had before. I create 3 shapes. I put them in a list. And now I just say, I loop through the shapes, and to each figure in figures, I say get area. And this is the magic of object-oriented programming. We'll dwell on this magic a little bit. Automatically, the correct get area behavior is invoked. Of course, because we placed it in the right location, but there is some elegance to this code, right? Because we'll just loop through and call get area on the object, and everything is taken care of for us. Same thing here, because we created customized double underscore dunder string methods, the print will also produce some nice stuff. So you can just run this code and see what happens. So hopefully all of you are yeah, there's a couple of typos here. Okay, so hopefully all of you are running this code, and yeah. Yeah, all of you are running this code, and I'll just give you a second. Please take a moment. Please take a moment and play with this code. It's probably the first time you're seeing objects. Scroll up and down, scroll through, and this would be a good moment to ask questions. I'll wait for another minute just to give you time to look at this stuff. Because after this, now we'll get into some of the nuances and start reflecting on classes and objects a little bit more. Okay. Okay, quick poll, I guess. So at this moment, okay, so we're going to go into a little bit more detail on this, but this is the first quick brain dump on objects and classes. So how does everyone feel about these classes and objects? Of course, we solved a simple problem here. I don't know how many of you have noticed the elegance or the lack of elegance of this code. So I think the poll was all about this last thing here, right? You used objects to solve a problem. What's your impression at this moment? I mean, just to contrast it, I showed you the function-based version of this code. So, okay, my response a long time ago was they're cool. Some of you want to think about it. That's always good. Reserve time for judgment. Okay, I will try to make it a little bit more natural. Okay, there's at least one of you who says yeah, this is also a good response, by the way, right? And I think for those who are more advanced, definitely a challenge to us as programmers to really come up with good guidelines of when we shall use objects heavily and what they get us and buy us and so on. That would be subject for at least an hour worth of discussion, debate, details, etc. Okay, so okay, so let me go on. Okay, so a couple of things for those, especially for those who said, you know, it takes so much of code, blah blah blah. There is no escaping classes. Almost every programming language, well, broad statement, but certainly Python, you have to use classes at least, right? Because Python integers, doubles, floats, strings, they're all classes and objects. So we have to use them well, use them effectively. We have to know what are their properties or attributes, and we have to know what methods we can call on them, right? So there's no way to say, I don't want to touch objects. So that is kind of given to us, unless you go back to a language like C. So I have spent a lot of time in earlier languages like C, and it's very interesting. If you spend a lot of time writing code in C, eventually your code will find the natural objects in the domain. And you have to deal with this tension that in nature, there are objects. A circle is a thing. It has properties and behavior, and somehow your code has to model it. And if you don't have the structure of objects, what are you going to do with your circles? Well, you make it a tuple, and then you have get area sitting somewhere else, etc. Right? So spend some time thinking about these paradigms. It's very, very deep, profound stuff, enriching stuff, I think. I've spent years thinking about it and experimenting and exploring. Okay, so there's no escaping classes. Write a few of them and see what happens. I think that's the easiest thing without being too much in debate mode. Just write it, learn how to use it, to create a couple of classes. But now I have to say there are many, many techniques to use classes effectively. So just because you know about classes does not mean every time you sit down to write code, you have to create a class or anything. Maybe in the initial part of your journey, you can just consume classes created by other people and just write functions and variables and structured code, okay? And slowly, as you start to appreciate why you would design a class, then you get deeper into it. I do want to say that the people who dreamt up object-oriented programming strongly believed, like engineers, that we would design in software, like there's a nail, and there's a very standard nail. Now of maybe its length or it has certain properties, but once you fix those properties, all the nails are identical, right? Or as close to identical as machine tolerance would give you. And we thought that we would bring this idea. There would be, like going to a hardware store, we would go to a software store and we would pull off the shelf all the objects we need and just assemble them and make our software. So software was, at least the object-oriented people thought that we could build software like we assemble parts to make a machine. But again, something to think about. It turns out that when I say what is a student or what is a circle, we don't have a standard, right? Everybody makes their own student and their own circle. So that whole vision did not materialize. And it's a deeper discussion. Why did it not materialize? Will it materialize in the future, etc. But anyway, so I would say, in programming, good design is key, but in object-oriented programming, even more so, because we are trying to design the industrial strength nail. And if you get it right, then there's tremendous benefit to the community. If you don't get it right, then everyone suffers, right? So there's a lot of thought process here. So a lot more upfront design and planning goes in object-oriented programming, I think, if you want to make it useful. Now, the other thing I want to say as a brief note here, there's a whole paradigm here of what are called using frameworks. Again, I introduced this kind of with a little pain because we use this in unit testing. So what is a big difference here is that a framework is a package or a Python library that you can't just call functions on it. It requires you to create, now we'll talk about subclasses in a minute, but it requires you to create the subclass of a class. And this voodoo that we do here is actually object-oriented programming, but now our code becomes part of a framework. As soon as I show you subclasses, please come back and look at this code and it will all make sense, okay? So I just put it here because I'm saying your exposure to objects will be or needs to be at least consuming pre-created classes and objects from libraries, and optionally in some cases, implementing some specific behavior in frameworks. Okay, and we have already done a lot of this, but now you start to see the meaning in it. Okay, quick, as much as I could do. Again, a little theory for those who have already known this. If I give any insight, do chat and tell me if I've said anything slightly different, okay? But everything I'm saying here is based on years of working with these things, right? So it's kind of my practitioner's point of view. So so why are we doing all this? Maybe that's another way to ask this question. And the idea is, well, there are three things we get. The first thing is this idea called encapsulation. And there's a kind of petty or simple definition of encapsulation. Everything that's defined inside a code, inside a class, is hidden from the outside world. You can only, or you should only go through the exposed functions and access, or the exposed properties and access them. So there could be a lot of internals to the class that are kept hidden. And there's this whole discussion for those of you who study Java or C++, what are called private variables and information hiding using private and public and so on. While that is very important and can again become a whole long discussion, I want to stress to all of you, start thinking about why exactly are we hiding things from external consumers of a class? And the answer is, if everybody comes into a class and starts using every property internally to a class, then when you change anything, everyone gets affected, right? So a beautiful example of encapsulation for us is in a car, the engine is kept encapsulated from you, right? Nobody opens it up, I mean, until you have to, but nobody opens it up and fiddles with it. So it's well encapsulated, and that gives us, a tremendous amount of resilience, right? So encapsulation is good, but now I want to highlight, what are we encapsulating? We're hiding things inside classes so that the classes can evolve on their own, and all the consumers of the class will not be affected. If we can achieve this kind of hiding, then our software is very good. When new features have to be added, we will add them to classes in such a way that all existing consumers will not be broken, and new behavior will emerge kind of slowly and people can start using it. So that's kind of the big idea of encapsulation, right? So we want to basically encapsulate change. By change, I mean requirements changing, and the evolution of software change. This is a very profound statement, right? And we need an advanced class to make examples of this. And then the other thing is there is a thing called state, right? Objects have state internally to them. By state, I mean even just the radius, and the radius can be changed from one value to another. So the state of the object can change over time. And we want all external consumers to not have to deal with all the internals of state changes. So again, objects allow us to hide this. These are advanced comments, so some of it might, but be aware of it. Think about state at least. That could be helpful. The next one is this very, very powerful tool. It's called polymorphism. So let me just jump straight away to give you something concrete. You see this interesting piece of code we used when we made functions. It had this if branch or branches, and the length of this if branch was as big as the number of different classes we had. And so this is an example of what programmers would call a code smell. If I saw something like this, I would immediately be aware of the fact that this could become very, very large if I had a large number of shapes. And so we would have to ask the question, how can we simplify this? The second thing is this function getArea has become a centralized place in which all the area computations are done. So anytime anybody adds a new shape, you have to come and change this function. So this function is constantly being worked on. It's very brittle and fragile and so on and so forth, right? So that is a huge, source of breaks and bugs and so on in function-based coding, right? What happened? So you have to go back and look at the code now and say, what happened to this? I don't want to just switch this page. So please, if you want, you can click back to that object-oriented code. Where did this if statement go? When we wrote everything in terms of objects, even though we had a lot of code, there was no more if statement. There was no more place where there's a lot of switching based on whether your circle or square was done. That's all taken care of. All that plumbing is taken care of dynamically by Python now. And this is very, very powerful, right? That you can have a list of things. You can call the method on those things and automatically the right thing happens. You do not have to make centralized logical decisions about who needs to do what. Right? And that, if we can unlock this potential, that's the potential of the world of objects, right? One of the key potentials. Encapsulation is another one. And then I want to just give you two words here. When we look at this code, there are two measures of, badness, quote unquote, in code. One is complexity. And I think large if statements or large and getting larger if statements are a sign of complexity. And the other is coupling, right? Every time you add a figure, you have this function is coupled to every change relating to adding figures. So it's strongly coupled. So again, you might want to look at a code every time you write code and say, is there any complexity in my code? Is there a strong coupling in my code? And then how will I change it? Okay. And the idea is that in object-oriented programming, we have eliminated this if statement complexity by using polymorphic dispatch. And we have eliminated the coupling by letting each class compute its own area. Okay, so in a small snippet, I think I've tried to give you a flavor of the potential power of object-oriented programming. But I think, to be honest, that's all I could do in this short amount of time, okay? So now, since we talked about classes and data, I just want to give you a simple but important idea here, right? So let me just highlight this. It's a technical point, but I think it's important to know and also fixes the vocabulary of classes and instances. So notice here, I've created the same class circle, but now instead of adding variables in the init method, I have just defined a variable right in the body of the class, right? And the question is, what is this variable? And the idea is that this variable is like a universal variable. And this variable is shared across all instances of the class. Okay, and these are all, the radius is an example of what's called an object variable. Every instance gets a new copy of the radius. That's why we can have two circles with different radii. But all circles will have the same value on their instance counters. Okay, so again, ponder this. This is in languages like Java, these are called static variables or class variables. This is how it's done in Python. There's no decorator or anything. It just depends on where you place it. So quickly, let me just walk you through a visualization. This is a little clunky, maybe you can see it or not. So it's the same code. So you see here, I've done the same. I've just copied that code over here. So it is actually creating an instance counter. Its value is 0. Every time we create a class, an instance. So let me show it to you here. Every time, so look at this. It's actually, I'm not showing you just to make it obfuscated. I've shown you one example where we can actually use a class variable nicely. What is this example doing? It's setting up a counter, and this counter is responsible for counting how many circles have been created. Okay, so again, you should step back and think about this. Like if I have objects, and for some reason I want to know how many of these objects exist, how would I know that? I cannot go through every time in my code and keep some global variable and keep incrementing it. There is a nice way to do this here. You create a class variable, and then every time you instantiate or construct a class, you increment that counter by 1. And boom, just like magic, you have a global counter. If you access this variable, it will tell you how many instances of circle you have. So let's see if we can see that, but also this will allow us to visualize, what is happening inside Python. So as soon as we start creating the class, let's just create it. So here you can see this. Let me just pull this to the side. So you see that if you, I hope you can read this. A template has been created, right? And this template in Python has an init method. It has a _str method. It has a getArea function, and it has an instance counter, right? So this is the template from which all our objects will be created. And right now there are no objects, just the class definition. Python now understands this new type. So if we start proceeding down this path, you guys can run through the simulation, right? All of you have access to it. If you step through this, you see as soon as we start creating this, you see a circle instance has been created. Right now, this is the object. This is the class. So, and this is the object. Where is that coming from? It's coming from, let me show you. It's coming from here, right? When we create the circle of radius 5, that's where it's coming from, right? So this is the class. So again, this may be the clincher, right? This is the class. This is the object. And the object has, where we did that self.radius, you can see now this is actually the self.radius. This radius belongs to this instance. So if you create a second, instance of the class, then you will have more. So let me see. Yeah, I'm probably okay. Okay, this is a little fiddly, right, to see on screen. So why don't I let all of you play with it? But all you're going to see is that, okay, let me just go through this a little bit more. I'm sure I created another instance, so let me get there at least. Okay, here you go. So you see, I created a second instance of the circle, and now you can see this is the class. There are 2 instances. One has a radius 5 and one has a radius 10. Okay, I took some time to put this visualization together. So when you have a quiet moment, just click through all the steps, and you'll see exactly how this simple piece of code is processed by Python. Maybe you can just tell me, do these pictures help? This will be helpful for me going forward, at least. Do these pictures help for you to see how classes and objects are created and manipulated? Okay, at least, okay, excellent. So please play with this, okay? Just click through it a few times, and you can even draw it on paper and visualize this. In the beginning, this is very helpful, right? Otherwise, you're going to have a fuzzy idea. This helps make everything precise. Okay, so much for this. Now, inheritance. Okay, so the next idea here is, if there are classes, then potentially there are subclasses, right? What does that mean? That, there's a natural hierarchy. For example, there are people and then there are students, right? And every student is a person. So there are natural hierarchies, and there are base types and derived base types and child types or derived types, parent types and child types, right? So some different types of language. This just exists in nature, right? We can ask the question then, how do we do this in programming, and why do we do this, right? And the idea is that there are 3 essential things we do when we create child types in programming. The first is that we can inherit, by being the child of something, you inherit all of the DNA of the parent, right? You inherit all of the properties of the parent. So if the parent had some attributes, then I have the same attributes. If the parent had some behavior like method, like functions in it, then the child automatically has it. So we inherit, and therefore code is not duplicated, right? The child automatically gets all the code you've written for the parent. Then you can customize it. So if you don't like, so this is not something we can do easily with our DNA, but if you don't like the DNA you get from the parent, in programming at least, the child is allowed to say, I don't like the get area function of the parent, I will provide my own. Okay, and I will give you a good example we have seen already of this. The _dunder_stir method that we implemented on every one of our classes is such a behavior. It says, I don't like what I get by default from my parent, which happens to be just a base object. I will replace the dunder_stir with my own stir method, right? And then I will get a better display. So you get to inherit, then you get to customize it, and you get to add new behavior. Right, so every child can add new behavior to the child class, and so that seems like a beautiful paradigm for inheritance. Yes. Okay, so here's an example. Let us just look through this one. Let's just look through this one. What have we done here? Let me see. So here is the Okay, so actually, I don't know if I pasted it correctly. I probably have to. Okay. Okay, so we'll come back. So let me just do it here for now. I probably put it in the next section. No, I didn't. Okay. So okay, yeah, now I remember. Okay. So all the work is done here. So I hid it from myself and I'm like, where did the code go? Okay. So here's, just take a minute and then we will be done with this whole thing. We have created now in the shapes.py file, a hierarchy of types. This would be the end of my library if I wrote this properly. You have a base class, which is called figure. And I've set up this base class with a counter. So later I can count how many figures are there in total. Okay, I have customized. This one we'll come to later. Just skip this, okay, for now. There's some very, very profound. For those who are advanced programmers, please go ahead and try to understand what happened here, okay? And if you have a question, please ask me and I will explain. But for now, let me just hide this, okay? So there's a figure. It has its constructor. It really doesn't do anything, just it increments the internal counter variable. That's all it does. But now every shape inherits. It's a subtype of figure. So every circle is also a figure. This is how we create subtypes. You pass in the parent type in the definition of the subtype. I repeat again, to create a subtype, all you do is in the definition of the subtype, you pass in the parent type as a parameter. Okay, and then Python will automatically wire up the classes. So for example, if you see here, what have I done? When we do the init method of the circle, apart from setting the radius internally, I also call the init method of my parent. And when I call the init method of my parent, the count gets incremented for me magically. Right? So this is a very cool, very deep idea here, that the instantiation protocol of a subtype must take care of making sure the base type is properly constructed as well. And if it's done so, then your code will have lots of very cool properties. For example, I can just count how many instances of all figures exist. So the same thing then is copy paste for circle and rectangle. But now let's take this one step further. So I've created this circle. Now I've created a circle with a border. Okay, I hope my language is clear. Just imagine a circle, two concentric circles. The outer circle is like the border, right? Or some circular path, field with a path around it, which is also circular. So in order to define such a thing, I have the natural radius of the inner circle, and then I have an extra border with parameter. So you see now this circle with border is a subtype of circle. Circle with border is a circle, and it's also a figure, right? So it's a two-step hierarchy. You just, other than where it inherits from, you process it like any other class. So if you take out this thing, it will not inherit from circle. But if you have this, then it does inherit from circle. And because circle inherits from figure, the inheritance chain will be pushed up all the way. Now, in the init method, you have to make sure that the base classes are also sensibly constructed. Okay, because if you want to use those properties, then you have to make sure they're set up correctly. Okay, so this is all boilerplate stuff to construct the type correctly. Okay, and then you can start using it. Okay, now there's a very cool visualization here. Actually, because it's kind of big, I will open it here. There's a lot of nice, interesting things here, but maybe you can just play with this in your own time, right? And just understand what happens here. Okay, I've created a bunch of objects and so on, and just have at it. But at this moment, if you play with it or have questions, ask me. Okay. Okay. So in a quick snapshot, we've covered the amazing world of object-oriented programming. Okay. So what are the takeaways? Some suggestions from me, at least, is, right now, as you go back to writing code, be more aware of all the classes that you are using and consuming. When you encounter new packages and libraries, again, be aware of what the classes are and what their properties are. Try to understand relationships and structures between those classes, if they have hierarchies and so on. Then on the side, you can start writing small. I mean, it's very hard, honestly, to get real toy examples. They'll give you examples like animals, and then a dog is an animal and so on. And it has one method called make sound, and it says bow or something. I don't know, just try to create something. But of course, where I found it extremely useful was modeling financial instruments, for example. And then you create a very sophisticated hierarchy. So you try to ask questions like, is a derivative different from an option? And if the option is a subtype, or what, is the derivative different from a bond, etc. Right? So you have to actually go through the whole class of financial products and come up with a sensible hierarchy. Those kind of efforts are very elaborate. That's where the real magic is, but maybe challenging at the moment. Some of you have finance background, so you might want to go there and think about what are the natural hierarchies and structures. As a programmer, how would you model all of that? Then, of course, for those who find this a little overwhelming, don't worry. You can write a lot of good code just by calling functions and just using all the available objects that have been created for you. So there's a long way to go before you run out of things to do or you're handicapped. And then there is one idea here about interfaces or abstract base classes. This is a little bit abstract in Python. So we will defer this for another time. Right, and I hope that all of you will join us in another course, etc., and then we can explore this. Okay, so I'm going to switch now to our next topic, which is actually I have a choice here. We could talk about strings for a little while, or we could talk about version control. Can somebody tell me which one you would want to talk about? Give me help. Strings or version control? I get like a 1-point sample of the class, but okay. Who's going to tell me? Come on. Okay, version control. Okay, so we'll do that. By the way, can I just tell all of you to come back with me quickly? I just want to take us. Okay, excellent. I will do that. So if you can come back just quickly to section 7, I have sent out an email yesterday, but if you click on this link here, I've created a small survey for all of you to take. I think it's kind of, it's kind of really important for me to get some feedback from all of you. I've put in a lot of time to try to make sure that this course actually caters to or gives you interesting experiences and takes you further on your journey. So if you can take a few minutes now or later just to fill out this survey, I would much appreciate it. And I painfully read every line you write because that's very valuable for me. So please give me 10, 15 minutes of your time to fill out this survey when you get a moment. Okay, so version control. Yes, yes, I think it's a very beautiful subject. I approach it with a little bit of what shall I say, trepidation, because it's not easy thing for me to simulate. So I'm going to have to walk you through and talk you through a lot of things, ideas mostly. And I have given very detailed instructions for all of you to do this. Remember, I try not to do anything too theoretical. I want you to always be doing something. But before I go any further, okay, so some people already asked this question, but can you quickly take this poll for me so I can see, see your background, how many of you are familiar with version control? So this is in the section 7A, titled What is Version Control? At the bottom, there's a poll. Can all of you quickly give me some feedback? I'll give you 10-20 seconds to respond to this. Okay, not at all familiar, very familiar. Okay, so there's a bunch of you. So those who know this stuff, please share, okay? I don't have to be the only person talking. So, okay, so let me start with what is this idea, okay? So the idea of version control is that we work with a lot of code, we have a lot of files, and we keep making changes to them. And the question is, sometimes when you make a lot of changes, you could break your code and you would probably want to go back to a previous version of your code. Also in a production environment, like if you're in a company making software, if you make a certain release of code, then you continue working and adding new features. If there's a bug in the code, you want to just fix the bug. You don't want to send out all the new features, right? So if it's iOS, whatever, X, and now the new version is iOS Y, but there's a bug in iOS X, then what we do is we want to send out iOS X.1, which has fixed the bugs. We don't necessarily want to send out iOS Y version, right? So that means that we have to basically make a lot of copies of our code, and keeping all these copies in sync eventually becomes impossible. Even for a single person, it becomes difficult. But now imagine how much more complicated it would be if you have a team of 100 people, all of them changing code at the same time, right? It would be just completely unmanageable. So that's the whole idea of version control, right? That it's a structure that allows us to continuously work on code, but at the same time, keep different versions and ability to roll back and go back to, old states or different states of the code so that we can have very targeted deployments or usage of code. Okay, so that's in a nutshell. So what are some of the features we want? We want to be able to, so by version, think of it as making copy. Okay, so now we had to ask this question, is every version a full copy? Right? So when I started programming and I didn't have version control, and probably some of you do this, if you want to do anything, you have 10 files, if you want to make changes, you just make a new folder and copy the whole thing over, right? And then you copy the whole thing over again. And there's no way for you to push changes from the starting version into the second one if you go and modify the original one, etc. Right? So, but anyway, you could think of versions as copies with some numbering system associated with it, right? 1, 2, 3, 4, 5. But actually, version control systems are much more efficient than that. Okay, and I won't get into the technology of it, but at the end of the day, it does provide you with such a labeling scheme that you can have multiple copies, each of them with some kind of label, not necessarily numerical. They actually typically use some kind of hashed values, but we won't think of it as a number for now. It doesn't matter. And then we are able to go to every copy of ours whenever we want, and we can pick and choose features from any of these copies and make a new copy out of it, right? We can merge all the changes. So you could take, the first file from version 0, the second file from version 1, the third file from version 2, and put it all together, and you can have a new situation, right? So it's kind of a very cool thing. It's also time travel in programming world, right? You can go back in time and see how was my code 10 years ago. Something I wish we could have in life, but we can't, right? You can't time travel. But here you do get time travel. So those are the features. And now by now you can ask the question, okay, that starts to seem interesting. How hard and complicated might it be? Of course, I have to alert you that none of this will work if you're not organized in how you want to organize it in your head, right? The second thing here is multiple users. So we want to put our code in some place where multiple people can get at it. And so the baby attempt would be just copy the folder on Dropbox or G Drive or iCloud. And then you can share it to multiple people. But now you can see the mess will be on iCloud because everybody will start creating their own copies, their own folders, and become unmanageable, right? So collaboration is key functionality that we want to get from version control. And of course, collaboration where people can work simultaneously, right? You don't want to say, hey, I'm working on it, all of you stop, I'm going to lock the folder now. We want people to be able to work simultaneously and then bring in all the changes together. Okay, I've just labeled this, you can read it, but how is all this voodoo going to work? Does anyone think this is going to work at this point when we put all these features down? Sounds nice, but is it going to work? And the answer is, for those who have used it, you will say, of course, yes, it works. Okay, so I just want to say that what we're using is called Git. Today, at least in the class, we will talk about Git and GitHub. So Git is a localized version control system. It lives on your machine, and it allows you to put files into folders, and it will keep a full historical track of all the changes that you want it to track. You have to tell it what to track, but then it will track it for you. And Git actually, by the way, is a beautiful example for me of what a powerful programmer can do. Those of you who use Linux are familiar with Linus. Linus Torvalds created the Linux kernel. And he had a real problem here because the kernel was worked on by a bunch of open source developers, and he couldn't really manage simultaneous developments. And he was frustrated with the available version control software. So in an amazing feat, he just sat down, he ranted about it once, and then he just sat down and wrote a solution. I think that can be a wonderful inspiration to all of us, right? When things bother us, maybe we can rant about it once, and then we should just solve the problem. That would be nice. So anyway, so you can spend some time, I've given you a link, go look up the history of it. I think it's a very beautiful metaphor of how we can make progress by clarity of thought. And Git was just fantastic in the ways that it moved version control software into the next generation. Why is it called Git? You can read about it. It's kind of humorous. Okay. So let's. So what is GitHub then? So a bunch of enterprising people came and said, okay, you can have Git on your machine running locally, but the real goal of Git was to make collaborative work. So why don't we take Git and we will host it in the cloud, and all of you can get access to a cloud-hosted version control system where collaboration can be done. And that is GitHub. Recently was acquired by Microsoft. We can talk about the business potentials, etc. But anyway, so here we are with Git and GitHub. Okay. So the first thing, so now theory is done, practical, right? But unfortunately, this practical requires some clicking and account creation and so on. So if you click on this link, you can just go to GitHub, and it's free, and they even have some extra packages for students and so on. So join GitHub for free. Please go in here and create your own account. In a minute, I will tell you why you should do this, okay? But I'll try to tell you why you should do this. So you can create an account very quickly, and you can become a GitHub member, okay? Choose a nice login name and an appropriate email and so on, and you can set it up. They have some extra packages for students, which I don't think you should explore right now. Just create a basic account and you're good to go. Okay, so after you've done this, the next step you have to do is you have to install Git itself. So GitHub is the picture is GitHub is a thing that lives in the cloud where you can push all your code to and live there. And then locally you will install Git, okay? And to install Git locally, you will just go to this site, and then based on your operating system, install locally, okay? After this, so that's the problem with this class. Unfortunately, all of you have to do it, and I will just show you what you can see here. So once you have installed it, I think I've given very explicit instructions. My suggestion to all of you is, if you have a half an hour to an hour, just sit down sometime, after this class or this weekend and do it. And then on Monday in the office hours, or if you need help, just reach out to me. And there can be some small bugs because something was not typed correctly or something, but in general, it should be fairly straightforward. And for those who are experts on the class, maybe you can share your expertise with your classmates too. Okay, so once you've set up Git, what is really nice is if you're on a Windows machine, Git actually comes with a Unix terminal emulator, let's call it that, right? So you can actually, on this terminal, no, Kristen is like, oh my God, you have to do all this for the labs. No, I have not put anything in the labs for you to do this. But please don't make that a reason not to do it, okay? I will talk about in a minute why we should do this. So yes, you can breathe the sigh of relief. No, you don't have to do any of this for the labs. And by the way, all the content of the labs are negotiable. So if you want to talk about anything, just come back to me, okay? I will walk through please remind me towards the end, I will walk through the labs that are due for this class. I've tried to make them relatively light, so since some of you have catch up to do, etc. So let's see how you feel about it. Okay, so what? Maybe I'm not going to teach you this so much as saying, look, I've given you all the instructions to follow. So you open up this terminal and you type in this git config. So git config allows us to set up the config locally. Okay, and then you just specify your username and your email, and now git is configured locally. Okay, so you're set up and ready to go. Now let's see what magic can we create. So the magic is actually kind of nice. First of all, you create a repository. Okay, so you can create a repository once you have an account on GitHub. Let's go through with the GitHub workflow. Okay, you can also create repositories locally, but we can come to that later if you want to do this. So maybe this is a moment for me to take a step back and say, why are we discussing this? So there are two important reasons, at least two, if not more important reasons why it's worthwhile for you as students to do this. Maybe three reasons. Reason number one is, yes, you can really organize all the code you write going forward from now. That's reason number one. Reason number two is that your GitHub repositories, just like your LinkedIn page, can become a storage place where potential employers can see what you're capable of doing. And this has become a standard, pretty standard recruiting thing. Like even at very senior levels, just like they will ask for your LinkedIn page, they will ask you, do you have a GitHub profile? So they can quickly see whether you've actually done some code and what your code looks like and so on and so forth. So for those of you who are interested in this, this is probably not a bad thing to make a start, right? Start writing some libraries, showing your capabilities and posting it on GitHub. And you have the option, I think, to make some of them private, some of them public. I haven't played too much with visibility, okay? But anyway, if you want to share it with other people, then as a part of your profile, then probably it's important. And the last and most important, well, actually, okay, since we're talking about employers, when you join any company, either in a management role or in a testing role or whatever role you might be, or a developer role, there will always be some form of version control. And so showing that you know how to use it will be a big asset for you in your job search and subsequently in your jobs, right? So this is very worthwhile learning for those reasons. And then the last reason, for those of you who are more advanced and adventurous, this is the mechanism by which you can join any open source project that's out there, right? So for example, Jupyter Notebooks, you can just, clone the Jupyter repository, and now you have the same code that the developers are working on. So there are even Python for that matter. You can get the Python source code and start working on it. And that's a wonderful thing to give back to the community, to get some visibility, to get some credibility, and even just to look at what a big software code looks like. These are all things you can do pretty easily from GitHub. You can search for some important repositories and start working on them, right? So for all these reasons, maybe since I talked about it for 5 minutes or 3 minutes, does anyone feel like, okay, maybe they'll give it a look, or you're like, okay, we could... I hope I have made some. Some good reasons for you to at least be conversant with it, right? I don't know how much each of you will end up using it, but I think today it's probably very important. Okay, having said all that, let's just do the practical thing. Yeah, not sure how. Yeah. I mean, okay, so there is another cool thing here, okay? If you step back and think about this problem, how will I create versions for all kinds of files and folders all over the place? Then Git is showing us how this idea can get executed beautifully, right? So just be conversant with it. I think if you spend a few days, you'll get enough. And in this course, I've shown you everything you need. So in a couple of pages, I've given you everything you need. So let me just talk you through the last couple of steps, and then you guys should try it and then come back to me with questions. Okay, so what are the steps? So the first thing you do is you can create your own repository, or you can clone someone else's repository. So let's just work in our own space for now. You create a repository and then you clone it. How do you clone it? You just say locally on your terminal, you run the command git clone, and then you pass the path to this repository, right? With the HTTP URL of this repository. As soon as you run this command, that repository will get cloned locally on your machine, right? And now you can start working on it. It behaves like like any folder you have on your machine. So you will know nothing when you work with Git that it's not an ordinary folder. Okay. Only thing is, when your work is complete, you have these extra 3 commands that you can run. And this is where all the magic is. So it's kind of cool, right? That all that complex stuff about versioning is just summarized into these 3 little commands. So what is it? And this is what makes Git cool and this whole story cool, right? If it was more complicated than that, we probably would not use it. So what do? You say git add minus all. So I've used the minus all because just to make your life easy, but git add minus all will include all the files that are currently in the folder and take a snapshot of it, right? And it's going to take a snapshot. It's ready to take a snapshot at this point. The next one is you say git commit, and then you pass in a message, whatever message you want that labels the work you've just done, right? It could be an initial commit, it could have been finish problem 2 or problem 3. It could be anything you wanted to label this particular version with. It's like a name, a friendly name and friendly information to you. And then you run this thing, git push minus u origin master. So let me just explain what we're doing. So now we have got a snapshot locally. We now want to push it back to the GitHub repository. So you commit the changes. That means Git now knows what constitutes this particular version. And then you push the changes. So when you say git push, you have to specify where it gets pushed to. And here this says push it back to the master branch. We'll talk about branches later, but it gets pushed to my repository. And then you're done. And boom, if you log into the Git repo, you can just see, right? You can just see your code in the repository, okay? And now let me just make something a little bit more elaborate. So here's the deal. I've actually given you all of the instructions. I've even taken all the screenshots and everything for you, but I don't want to overwhelm. This is one of those things. I don't know if my words are going to add any benefit to it, but what I'm going to say right now probably does, which is, okay, what are the steps? Or how do we do the steps? And the steps here is, when we want to collaborate with other people, what are the steps I should take? So let me just talk you through that. First, you get the URL of which repository you want. And then you basically use, there's a button, once you go to any repository on GitHub, there will be a button on this page which says fork the project. So the first idea is this idea of forking the project. And this kind of a programmer speak, but basically what it does is it copies that project into your repository. So forking puts that project into your repository. Okay, and I've kind of mentioned that there. So you now have it in your repo, and now you can just basically git clone it. So now you get a local copy on your machine. And this is really cool. You can disconnect from the internet and start working locally. You can be on a plane, you can be anywhere, on a beach. Finish your work, and then you do exactly what we discussed right now. You git add the files you've changed, you git commit it, and when you get an internet connection, you basically push, right? So you clone and work locally. When you finished all your changes, you push it, but now you push it to the fork. So the code is now living on the GitHub fork in your repository. Now you need to send it to the owner, right, of this project and say, hey, I made some changes. Can you please take my changes and put it in to the main branch, main work, right? For if it's an open source project, you're contributing now to the open source project. This idea of bringing forks and the original together are accomplished by what are called pull requests. So there's a little button as soon as you go to your repository. If you're working on a fork, there will be a button that says submit pull request. You just click on that button and say, you know, you can give some explanatory, there's a text box where you can explain what you've worked on, and you're done. Now the owner of the repo will get notified, and he will be able to just bring all your changes into the main repo. Now there are automatic changes if you've added new files, blah, 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 where they don't overlap. But there are also places where it's conflict, right? So for example, if there's a buggy line of code and you've written a new line of code, the person who's merging the changes will be able to see the difference between the two files and selectively choose what he wants to incorporate. So this is very cool. It's called the merge process. Sometimes it's manual, sometimes it can be automatic if you have no conflicts, which a human has to resolve and pick which is the right thing to do. But then the codes are merged and then you're done, basically. Okay, so I think for all of you, if you just work on this forked master, if you get this far, you know, you create repositories, you clone them locally, you push the changes. And then the second step is you get someone else's repository, you fork it, and then you work on it and push changes. Then I think you kind of masters of Git. Okay, and since I said all this, I will just say that in the later when I go to the assignments, we can talk about it. in the assignment, I've given you a particular repository. If you have the energy, go through this and try to fork that repository, put some changes and push it. I will do the merges and tell you if you're successful, etc. Okay, that's just extra credit. You don't have to do it. Okay. Okay, so let me quickly see. Any questions on version control? Let's go quick, so because I have to talk about one more topic. Clear, unclear, need more time? Someone? Seems okay. Okay, yeah, I don't think it should feel totally natural. Honestly, if you take 10, 15 minutes, yes, that's good, Mitch. Yeah, just take an afternoon. It's mostly installs and then a couple of commands. I think I have tried to be very explicit on what you need to do, so you don't need to go all over the web and search for instructions. Try to follow it. If you get stuck anywhere, I'm happy to jump on a call and share screen and we can fix it. Plus on Monday, which is the last office hours, if you want to come and discuss, I'm happy to do that too. Okay, so here's what I can say. As a piece of software, it's a wonderful piece of software. As I stressed to you, it has very many applications, in your career. So it's probably worth a little bit of time. Okay, so the last thing and the easy thing, right? So I don't need to really spend much time here as to call your attention to this. I just want to say that, one of the workhorses of the work we have done used so far is strings, right? And so I just want to call your attention to this idea. Just go through this thinking pattern every time I do this when I encounter a new collection. Think about what the definition. So for example, let's apply the strings. What is the definition of a string? How do I create strings? How can I access elements of the strings? How do I modify strings? How can I iterate through the characters in a string? How can I count the number or the length of a string, right? So you go through this thing, make sure that you can do this, right? Think of this like a small assignment, just take some examples. So what I have done here, and you can tell me if you need me to talk through it, I'll ask you in a poll in a second. I've just created examples of all these things, right? How to use strings. So quick poll, what's the situation with strings for all of you? Very familiar, slightly familiar. I expect all of you are like experts now, but I could not leave this session without mentioning strings. Okay, hopefully you've all clicked on it. Okay, there's only one, maybe one person, right? So, okay, so what am I going to say? So I won't spend much time therefore. Yeah, and also we're a little low on time. So what am I going to say? I'm going to say that the information here is extremely self-contained and explanatory, right? So if you have 10 minutes to just read through this, I think it should be easy. There's not a whole lot, like for example, how do I add variables to a string? We've already used the string.format quite a lot. So, okay, sorry. So when you look at this code, it should be very self-explanatory for you, what's going on here. But still for completeness, I have included it, and also for a moment for you to think about it, okay? But I want to highlight here, for example, strings cannot be modified, okay? And if you run through this visualization, you'll see that, okay, so I'll make this is a very powerful idea. If there is a type that cannot be modified, this means that in your whole program, if there is a class that cannot be modified, in your whole program, you need to have only one instance of that class. So what is an example of that? The string that cannot be modified is a very particular, suppose there's a string called hello, like this. There needs to be only one hello in the whole program. There needs to be only one hello world in the whole program. Everybody who needs the string hello can share this one instance of hello, right? And that's a tremendous efficiency boost if the object is immutable. The moment the object is mutable and you can add a character to the string, now copies have to be created. And so in Python, the classes are not, this is a detail here, but just think about mutability and immutability. And the fact that string instances like hello are shared across all consumers. And so you cannot actually index into a string and change a character there. You basically have to create a new string. So this is the one big difference between lists, which are mutable, where you can take a list and put an index, and then suppose I have a list 1, 2, 3, 4, 5, you can go to the third element and make it 100, right? This will work. The index operator will not work the same way in string. So that is a important feature of strings that I want to call to your attention. Here I will talk about, okay, so this is also very important. If you click on this link, I just want to take you here right now. Please click on this link. It takes you directly to the Python documentation. And I must tell you this, the Python documentation is actually very well written. It is probably one of the best places, in my opinion, to learn Python. It's very precise, it's clear, there's lots of examples. So please, wherever possible, go to the documentation. And what is nice, I'll just show you one more thing, navigating the documentation. The documentation also allows you to have a drop down here and you can pick the appropriate Python version. And as you can see, there's a lot of stuff in the Python standard library, right? And programming languages are interesting or capable based on what the libraries provide. Okay, so after that, you can basically go here. There are some simple patterns here that are given. This is true for any collection, but you can just apply these patterns to strings. So this becomes just a simple exercise. Go through this thing and try each one of these out. Replace collection with a particular string, and I've given you examples in here. I don't need to run through it. But I want to call your attention to something very important, and I've given an assignment on this, so I must call your attention to it. You can split a piece of text using the split command, and then you can do all kinds of interesting also methods on the string. For example, you can do upper, and you can do lower, and you can do capitalize, right? So there are functions you can call. Get familiar with this function. I've given you one exercise in the lab that requires you to manipulate strings. In particular, it requires you, we did an old assignment where I'd given you the text of a speech, and then I'd asked you to find how many distinct words are there and count them. But now I would like you to make them all lowercase so that, uppercase and lowercase are not considered distinct, capitals are ignored, and eliminate all punctuations, right? So then the word count will be a little bit more sensible. I skipped that step because we had not learned about strings, but now that you know how to play with strings, you can do, I think everything that you need to do that assignment is in here in examples. Okay, so just play with this before you attempt that exercise, but it's not too hard. I do want to say this thing about string slicing quickly, that the slices in strings work exactly like the slices in lists. So if you've been manipulating lists, they have this idea. You can pass in a starting point, a stopping point, and a stepping point. It's pretty much also like range. So this pattern is repeated here. So you can use this to manipulate strings, okay? The one thing I will repeat is always be clear whether you're modifying a string or you're getting back a new string. This must be clear when you're manipulating strings, okay? There's a little exploration here for you to write some code to find a palindrome. I have given you the solution, so play with it. Oh, I have not given you the solution. So play with it. If you need it, we can discuss. It's a one-liner, by the way. And then string formats, right? So this dot format, again, you can read this, it's not very hard. So I kind of walked through strings a little bit fast, but I just wanted to do this to say, it's not that hard now that you guys are, that all of you are where you are. The idea of recognizing that a string is a new class, there's a way to construct it, it has standard methods. Using strings becomes hopefully second nature to you. But it will not come without sitting and typing a little bit, making a few mistakes and fixing it and becoming proficient. Okay, so please do that. I don't think my words are going to help that much. Okay, so it's time to wind up, I think. Okay, so let me just see, did I say anything in terms of summary? I think I put a couple of things. Are there any questions at this point? Quickly. I have to say to all of you, you've been a wonderful bunch. I really loved working with all of you. I do wish I could get a little bit more comments, but okay. At least send me emails. Please take the surveys so I can hear from you. I really value it. Let me just see. And I have one last thing. I will just point it out to you. Okay, yeah. So I have one last thing here. Let me try to cram it in just because, okay? It's just because I think I can simplify it to just a 2-minute explanation here. So I thought it would not be good for us to leave this course without thinking about errors. So what are errors? There are three types of errors that we could put there. Maybe there are more, but let's just think about it. There are syntax errors and there are logic errors. Syntax errors you fix usually when you start trying to run your code, like missing a parenthesis or something like that, not closing a bracket. Logic errors are harder. You have to write unit tests and understand your code to fix logic errors. But then there are things like exceptions, right? Sudden unexpected behavior. I've created a good, let me just change the font quickly just to show you this. I've created a good example of this. Suppose you're getting a number from a user, and whatever the user enters, I want to use it as a denominator. So I want to take some numerator, which could be 1, and divide by a number given by the user, make a fraction out of it. Now, if the user enters 0, we're going to have trouble, right? So please play with this code and see, first think about what will you do. If a user enters 0, I'll get 1 divided by 0, which is going to blow up. Right now, if you don't do anything, your program will just crash, and that would not be a good thing. So what you need to do is then handle this division by 0 problem. And Python gives you, and all programming languages give you, a very powerful metaphor for dealing with this. So stay with me for 2 minutes and I will share this metaphor. There's more to explore, of course. So what you do is you use this try, except structure. First, let's just focus on try and except, okay? So it's like an if statement, basically. You try to do something, and this could be many lines of code, many function calls. You try to do something. And what Python says is, if you fail in what you're trying to do, I will not crash the program. I'll give you one chance to recover. And I will go to this except block. And in this except block, you can do everything that is possible to fix the situation, right? And if you fix the situation, you could probably go back to the user and give it a message. And so use this to try to fix this interaction, okay? And as consumers of software, you know, sometimes things go into a bad state. Try to use this example to fix this particular small program, right? Calculate the division by a number n. N is 0. What will we do? So you try to divide. If it fails, you have a chance to recover here. I have not fully implemented the recovery. I've just printed a message saying something bad happened, okay? And for now, I would say to you, you don't need this extra stuff. I just put it here for completeness. Just work with the try and except, okay? And that would be a great start. Because it takes some time to think about exceptions and how to handle them. And I would also say, do not treat this like an if-else branch, okay? Because it's much more profound than an if-else branch. In fact, exceptions are a class in Python, and there's a whole hierarchy of exceptions. But it would take us, since we just learned object-oriented programming, it doesn't help for me to teach you about exception hierarchies. But this is a very modern way of handling errors in code. That is for an advanced course for sure, because it involves an object hierarchy and handling exceptions well. But at a very simple level, if you have code that you're afraid it's going to fail, you could just do this, okay? Now, there is an anti-pattern here that I will mention. You could just do this and say, you know what, try to do my code. If it fails, just don't do anything but don't crash. But this would probably be a very bad pattern, because the error will now disappear into hot air. Nobody will ever be able to see what happened. So at the very minimum, you have to probably, you know, print out the message that comes from the error, okay? But that's about what I wanted to say. But this try except is, Python syntax is try except. Languages, for those who are familiarity with other languages like Java and so on, this would be try catch, okay? So I have to switch my mind to saying try except. But for those who are curious about these other branches are attempts to, you know, do processing outside of the exception branch, right? So you can always clean up here. So one beautiful exercise for you on this topic would be, go back to your database code. When you try to open a connection to the database, you should, suppose the database doesn't exist, the whole thing is going to crash. So you should put a try, technically you should put a try block around it, and then database not found, you should, you know, that message, Python will actually say some sensible message here. You can catch it and recover and do various things with it. So you could go and apply this in some simple situations. But I think this particular example, if you just keep on thinking about it and tweaking it, you will start to get a sense for exceptions and how hard they are. Because recovering from exceptions is not easy, right? I mean, you really have to know, like halfway in the program, something bad happened. Where do I need to restart, right? And that's the real hard work for a programmer. So for this beginner's course, I guess we just pretend we'll write good code, there will be no exceptions. But then for an intermediate course, we have to make all this very real and get better at using objects. Okay, so I gave you the last nugget that I could put into this course for you. I've tried to give you all a good flavor of various aspects of Python. Clearly, there's much more to be done. I hope we'll get a chance to work on an intermediate course or advanced course. I do want to say that if you put some time in and master this stuff, even if you have no interest in being a software developer, it will certainly change the way you think about things. It will change the way you interact with programs. It will change the way you interact with developers and programmers. And for sure, it will also even in some ways change the way you live your life, right? So I think there's a lot of benefits for all of you to invest. You've already done wonderfully well. So I want to congratulate all of you for sticking through the course and making it this far. So there's just this last stage, right? Finish off your quizzes and labs and get a great grade. And I'll be happy to send out all your certificates and everything. And I really look forward to working with you sometime in the future. But I think our time is up. There will be office hours again on Monday. Send me an email if you want to talk. I will follow up with an email as well. Yeah, yes. I will look at chat for any of your comments. Well, thank you all. So yeah, like I said, anything I can, yeah, you're a wonderful bunch. I just wish you would talk a little bit more and trouble me a little bit more with questions and emails. And you can still do that. I am here as a dedicated resource for all of you. So if there's any way I can help now, in future, discussing careers, anything, don't hesitate to reach out. Wish you all the best. We'll still be in touch for another couple of weeks. So yeah, thanks a lot.
Thanks, Vijay.